Okay, we derive the one-dimensional wave equation. For that purpose, we consider a string of length L that lies on x-axis. So we have x-axis here, and on that x-axis we have a string of length L, and we have y-axis as well. Now if we stretch the string upward, let's pull the string upward, we pull it up, what will happen? String will get stretched and it will acquire a kind of curved shape, or rather it will acquire some shape. And let us consider a chunk of string. Let us consider a chunk of string PQ. So we have a chunk of string PQ. Then let x with the x coordinate of P and x plus delta x with the x coordinate of Q. That means we take PQ to be a small chunk, and approximately it's of length delta x. Once again, we have P has x coordinate x and Q has x coordinate x plus delta x. Then what can we say about the forces that act on that chunk PQ? At the point P, we have tension that acts in this direction. Let's call it T1. At the point Q, we have a tension that acts in this direction. Let's call it T2. Let's break those tension along horizontal and vertical component. For that purpose, we introduce triangles alpha and beta. Okay, now we must balance the forces that exist along horizontal direction as well as vertical direction. We assume that air resistance is not there and gravity is not there, and so on. String is elastic, etc., etc. Now along x-axis, what do we have? Along x-axis, T1, if we take the horizontal component, then we have T1 cos alpha equal to, what about the horizontal component of T2? We have T2 cos beta. Are these equal? Yes. T1 cos alpha, that is the horizontal component of T1, and T2 cos beta, that is the horizontal component of T2, they must balance. You don't have any other forces along x-axis. And it's equal to some value, let's say T, and write it. Okay, let's say T. What about along vertical axis, along y-axis? Along y-axis, comma, well, T1 sin alpha, that is acting down. You have one force T1 sin alpha that is acting down, and you have T2 sine beta, T1 sine alpha. Let me write it in blue. We'll see it why. T1 sine alpha, that is acting down, and T2 sine beta. Do we have something else? Yes, we have. Before that, we have T1 sine alpha, that is acting down, T2 sine beta, that is acting up, and do we have some other forces? Yes, PQ is exerting some restoring force towards the mean position. And what is that? That is your mass into acceleration. If U denotes position of the string, then what is acceleration? That is acting down, mass into acceleration. M denotes mass of PQ. M into acceleration. What is acceleration? Well, that is del to U del T square. Differentiation of double differentiation of position with respect to time will give you acceleration. That is acting down. Now downward forces must balance with the upward forces, so you must have equality here. Let's write it in another form. We have T1 sine alpha minus U. Okay, minus, no problem, everything correct, T2 sine beta equal to minus M into del to U del T square. Okay, now we want to combine these two equations. Let's say this is equation star, and let's say this equation double star. Dividing by T throughout. Dividing by T throughout. Well, throughout means we divide each of this by T. What do we get? T1 sine alpha by T minus T2 sine beta by T equal to minus M by T del to U del T square. But by equation star, T is T1 cos alpha as well as T2 cos beta. Well, instead of T I can write T1 cos alpha. Instead of T I can also write T2 cos beta. So T1 sine alpha, in place of T I can write T1 cos alpha. Aha, so many things cancels. What about here? Well, the same thing happens. Quite a lot of things gets cancelled. Instead of T I can write T2 cos beta equal to minus M by T, right inside as it is. Let's cancel T1, T1, T2, T2. Now we know from trigonometry that sine by cos is 10. So you have 10 alpha minus 10 beta equal to minus M by T del to U del T square. Quite a simple relation. Also, What about mass, m? Let we assume the string to be of uniform density, that is its mass. Let's assume it to be unit density. Let rho be the mass per unit length of string. What does that mean? If rho is the mass per unit length of the string and string is of uniform density, then rho must remain constant. Then mass of that small chunk PQ must be equal to mass of PQ is density into length, linear density into length. Therefore, we can write above equation is so we can write this equation is therefore tan alpha minus tan beta equal to minus rho into delta x by t del 2u del t square. Why to keep minus here? Let's multiply by minus throughout. Tan alpha minus tan beta. Okay, we have just written instead of mass, density, linear density into delta x. Okay. Now let's multiply by minus throughout. So we have tan beta minus tan alpha equal to now we know that derivatives gives a slope of tangent, or tan alpha is nothing actually derivative at that point. In other words, we can write it as tan beta is nothing but del u by del x. But at what point? At q. So del u by del x at x plus delta x. What about tan alpha? Again derivative. So del u by del x at x equal to rho into delta x by t del 2u del t square. Okay, let's divide by delta x throughout. So we have just divided by delta x throughout and we got this. Now if we before we can take the limit, and or we can recall limit h tends to 0 f of x plus h minus fx by h is your f test x. If we write h is delta x, you have f of x plus delta x minus fx by delta x. So you have got this. Why don't we take the limit then? Taking limit is delta x tends to 0, we have limit delta x tends to 0 del u by del x evaluated at x plus delta x minus del u by del x evaluated at x divided by delta x equal to, right hand side as it is, rho by t del 2u del t square. Now you are taking the limit f of x plus h minus fx by h. That is your differentiation of f, but not with respect to t, only with respect to x, and so we are bound to use partial derivative once again. Del x of that f, and that f is del u by del x equal to rho by t del 2u by del t square. So that can be written as del 2u by del x square equal to rho by t del 2u by del t square. Now density is a constant and t is also a constant, and these are actually positive, and they are generally written on the left hand side. That's what standard convention is there. So that your work is simplified. Now this is a positive constant. Why should I? So okay, I can write it as c into del 2u by del x square equal to del 2u by del t square, where c is a positive constant. But why should I every time write where c is a positive constant, where c is a positive constant? Why don't I just write c square? Well, c square will always be a positive constant. So that's what the exact expression is for the 1D wave equation. Thank you.